SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 6. We were talking about a problem example where we wanted to make a selection decision between two different vendors from this company Rotor Dynamics, and there were certain criterion which were used for judging whether product A or B is better, and one of them was basically the ultimate tensile strength measured in kg force per millimeter square. There was a lower limit of this particular force which was given, exceeding, going below which would be a criticality and will not be acceptable in any case. And because it's ultimate tensile strength, we concluded that this would be a case where we'll use the larger the better kind of a quality system to calculate the losses. So let us first look at the results from the destructive testing of 20 specimens that Rotor Dynamics talks about between sample A and B, and the table illustrated here as can be seen is about both the products A and B, where about 20 specimens have been tested destructively for the bolts from suppliers A and B, and have been able to get a data of their ultimate tensile strength as represented here. This 15.5 for example in one case, 13.8 in another case, so on and so forth. And similarly for B, again these different entries are being made in this table which corresponds to the different ultimate tensile strength with reference to the sample number. So there are exactly 20 specimens of each type A and B which have been destructively tested, and we will use the average quality loss for the loss function Ly equal to k by y square in this particular case. Again reiterating that y being the ultimate tensile strength goes for larger the better. Okay, so we already know that the quality loss, the AQL, average quality loss in this particular case would be represented by 1 by mu square k times of 1 plus thrice sigma square by mu square, where mu again, if you may recall, was the process mean. So we are talking about I varying between 1 to n, 1 by n yi, and the square of sigma is representative of 1 by n minus 1 sigma I varying between 1 to n yi minus mu square. Okay, so the deviation of the quality characteristic. So having said that, if I wanted to look at this particular table and see what is the process mean for A, so let that be mu A, and what is the process mean for B, let that be mu B, and similarly the standard deviations for A and B be sigma A and sigma B. So from the first principles, using these different formulations given here, if you calculate from these 20 samples of each type, you get the process mean for A accordingly as 14.66 kg per millimeter square, and the sigma of A, the standard deviation of the distribution A, as 0.656, and similarly the process mean for B is 14.41 this particular case, and sigma B comes out to be 2.327 in this particular case. For larger the better type, of quality characteristics the estimation of K values is based on the lower specification limit, which in this particular case corresponds to the value d equal to 11 kg per millimeter square. Okay. So, this is minimum amount of ultimate shear strength which is needed in this particular case for qualifying a bolt to be acceptable. Okay. So, therefore, the Ka value here comes out to be from the loss function, in this particular case, because the loss function Ly is K by y square. So, the Ka really is equal to the unit cost A times of square of y, where y is 11 in this particular case, y equal to d is 11 in this particular case. So, here we can say the Ka value comes out to be equal to the loss function, which is the unit cost of repair in case of bolt failure, and such an unit cost per system comes out to be $15. If you look at the problem example, the system requires highly reliable bolts, and in case of bolt failures, system repair cost is estimated to be $15. Okay. So, having said that, we can actually try to calculate the loss constant for the product A and B, and this would be again the value for A, the unit cost for the system when the bolt failure happens, times of square of the minimum specification. Okay. So, 11 square, and same is true for, because there is similar kind of lower tolerance limit for both the cases A and B. You have the similar kind of K factors in both the cases. So, this comes out to be 1815. Okay. Dollar kg force mm square. So, you have to understand this is something that it can create a variability. Supposing you had a vendor who was not very good in producing a certain minimum thresholding of 11 kg force per millimeter square required by the company, you could always lower the or you could always higher the d value for the particular vendor from 11 to, let us say, 13 or 14, so that always his loss constant would be higher. Okay. So, that way it will give you a sort of a bias on that vendor, that if you are not able to tightly control the ultimate tensile strength property, then it will automatically be fading away, because your d value or the value that is needed for screening off the good from the bad bolts is much higher in comparison to the other vendor. Okay. So, you can intentionally do that also sometimes to create a ripple in the system, to eliminate a few vendors which for sure do not produce quality. But then again, it depends on, so obviously the intent has to be good in that particular case when you are doing a forced elimination of some vendors. So, having said that, now you can calculate the loss function of both components A and B. In this particular case, loss function, for example, of A can be reported as the Ka value times of 1 divided by the process mean mu A square times of 1 plus thrice the sigma value for A, which is 0.656, divided by the mu value 14.66 square, and this comes out to be equal to about close to $8.48 if you calculate this. Okay. So, we have merely put the value of mu A to be equal to 14.66, put the value of sigma A to be equal to 0.656 as you have seen earlier in these calculations, and the Ka value has been borrowed to be 1815 from the earlier step. So, similar kind of a analysis can be done for calculating the loss of product B. Here the value can be 1815 divided by 14.41 square, which is the new mean for the process B among the 20 observations of the specimens destructively tested earlier, divided times of 1 plus 3, 2.327 divided by 14.41 square. This is the mu B by sigma B square, okay, and this results in something like $9.40. Okay, therefore, if I wanted to take a management decision on the basis of this quality loss, so quality loss for the lot of 20,000 units of product A is obviously less than that of B. Okay. So, you can see here that LB here is higher than LA. LA earlier was $8.48 and this is $9.40. So, obviously, the first choice would be A, but you have to consider again another factor here which is very important, that also there is a question of overall cost that is coming here, and you are talking about 20,000 pieces or samples of a certain product. And if you look at earlier the cost of purchase of both the products, the A is actually an expensive product than B. So, obviously, although the B you are saying has a intentional loss or a virtual loss which gets added on to the system, and it is higher than probably $1 than what A would otherwise do in terms of losses. But you can see here that the overall unit cost of B is much lower in comparison, at least 1 cent lower in comparison to that of A, and there are about close to 20,000 cents which you are saving in a lot of 20,000 or in a batch of 20,000 specimens or samples that you are getting for the system. So, obviously, the management decision then would look at both these aspects, okay. And if purely the decision was on the basis of the loss factor, then you would definitely choose B, but then otherwise you are probably gaining about $200 by getting the cheaper component, whereas the loss difference here between A and B is not more than, let us say, $1.40. So, there is sometimes a realistic approach which is used. So, in that event probably although the loss of B is higher, B would still be a better choice in this particular case. Okay. So, I would just clearly write it here that therefore, based purely on a quality loss criteria, product A is preferable. However, if we consider only purchasing cost, product B is cheaper by $200 because of this 1 cent per piece difference between A and B, and 20,000 pieces being put on board for buying. So, a more realistic approach is to consider both the costs before taking a management decision. So, obviously, there would be a lot other factors which would be involved in this case. For example, It may be that the lead time for B is lower than A, or for example, even if we talk about the overall quality losses, there may not be more than 1 or 2 such events, or for the whole 20,000 there may be some database which says that there are at least 5 pieces failing or 6 pieces failing, and there the decision would be based on whether the $200 is higher or the number of times that you are incurring the loss because of putting B into the system or A into the system is higher. Okay. So, commensurate decision has to be made according to the data that is available in this particular circumstance. So, we have kind of understood how the quality loss function can be embedded into a system, although it is a virtual loss, but it is very, very important, and it is a governing criterion for sometimes taking decisions on a management scale, for particularly related to the in-house tolerance design or purchase of components or even process settings. Okay. And there can be many examples like this from the industry, where you can directly apply this quality loss, this virtual loss phenomena, to get an estimate of how you would otherwise sort of be able to choose one option over the other, because it's not giving you the kind of quality losses, or it's not giving you the kind of foolproof situations quality wise, okay, that comes out. So, having said that, then the next question is that when we design the system, there has to be various factors to design the system. Obviously, there is going to be an engineering noise behind such systems. There is also going to be a sort of a signal which would give you the required quality characteristic to go up to the desired value or intended value. There is also going to be a response based on the signal that you have given to a particular system, and there are responsible control factors which would guide the signal in a manner so that the response behaves in a certain aspect or certain way to the quality determinant or the quality characteristic determinant which has been planned. So, we will talk about these concepts in the next module, where we will discuss such engineering systems in terms of noise factors, control factors, signal factors and response factors, and then try to analyze a system's performance based on all these different measurable or non-measurable even qualitative factors which would be coupled into the system. So, thank you very much.